All right, general people, I wanted to talk about this problem because your book does something rather odd when it tries to give you the solution to this problem. When your book has a very, very, very large concentration on either the product or reactant side, they go ahead and say that there is no longer an equilibrium and we should treat this problem as a stoichiometric problem. And this confused a lot of people when looking at the solution. So I think this is an unnecessary approach and just adds extra steps when trying to solve this problem. So I'm going to show you that you can go ahead and treat this problem just like any other equilibrium problem, but all you have to do is just keep a few more significant figures. So let's go ahead and get started. So like I mentioned before, we're going to set up our ICE table. So let's write down our reaction. So this is the equilibrium we're interested in. Now they gave us a K value for this. So remember, when your book gives you a K and it doesn't put a subscript on it, you can assume that this is Kc. So the Kc here happens to be 1.1 times 10 to the third. We can go ahead and rewrite this as 1100. So now let's look at the things they add in our equilibrium. So the first thing they have is FeNO3, 3. So they tell you that they add 0.02 moles of this into a 1 liter solution, and doing this addition does not change the volume. So in essence, we can say that the concentration of FeNO3 is going to be 0.02 molar. Now what we'll note here is that this is an ionic compound, and so this is going to completely break up into iron 3 ions and NO3 ions. Now we don't care about the NO3, but we do care about those Fe3 plus ions. Because we're going to go ahead and do an ICE table, we can go ahead and put an initial amount of iron to be 0.02 molar. Now this is going to go into a KSCN solution. Now again, we need to look at the relevant ion. This is an ionic compound. It's going to completely break up, and the equilibrium deals with SCN minus. So since this was 0.1 molar, we know that SCN minus is going to be 0.1 molar. Now we didn't add any FeSCN2 plus, so this is going to be 0. So in this case, what we see is we're going to make products because we have 0 products. So I'm going to make products, and that means I'm going to consume reactants. So my products are going to have a positive change. My reactants are going to have a negative change. If we look at our stoichiometric coefficients, everything is in a 1-to-1 ratio. That means I'm going to have minus x to minus x to plus x, everything in a 1-to-1 ratio. So I plus C equals E, so 0.02 minus x, 0.1 minus x, and x are going to be my equilibrium concentrations. So let's go ahead and put this to the Kc value that we got. So Kc is going to be my products, so in this case x, over my reactants, so 0.02 minus x times 0.1 minus x. This all equals 1100, the Kc value given to us. So now we're going to do a little bit of math. We're going to go ahead and FOIL that bottom part out. And then what we can do is we can times both sides by that numerator. I can go ahead and distribute that 1100. And the final thing I can do is I can go ahead and combine like terms and make sure that my polynomial is equal to 0. So now what I can do is I can go ahead and put this into a quadratic equation solver, or I can use the quadratic equation formula. What you'll get is 2 values. Now, only one of the values is going to make sense. That value happens to be 0.01978. Now, the other x value that is generated, what you will note is if you subtract it from one of these equilibrium concentrations, you'll get a negative concentration. So you can't have a negative concentration. So that's why you know that number is unacceptable and a false solution. All right, let's go ahead and finish off this problem and plug our x into our equilibrium concentrations to get a numerical value out of them. So 0.02 minus x happens to be 2.2 times 10 to the negative fourth. 0.1 minus our x value is going to be 0.08022. And then finally, our x value, we can just write for our final concentration of 0.01978. So these are going to be the concentrations at equilibrium. All right, I hope that made sense to you all.